This eUnit is designed to be used by both sustainability managers reading or commissioning an LCA and LCA practitioners studying impact assessment methods. Because of this range of learners, we are providing this short overview of how you may want to navigate the materials contained in this eUnit, depending on if you are a manager or practitioner. The first chapter on how impact assessment methods model is intended for both managers and practitioners. The next chapters cover each impact category, and each have two sections, Understanding and Modeling. The Understanding section is intended for all learners, the Modeling section for practitioners, and managers who may want to take a deeper dive into the impact category. There are resources available for further reading and reference throughout this eUnit. Practitioners should review all these resources. Throughout the eUnit, a resource icon is shown when a resource is available on the section topic. Below is a catalog, and you can click on any of the resources to view them now. Click Next to get started. Eutrophication occurs when excessive amounts of nutrients reach aquatic and terrestrial ecosystems. In terrestrial systems, the addition of nutrients will change the species composition to favor those which benefit from higher levels of nutrients. In aquatic systems, the addition of nutrients has a similar primary impact by fertilizing the plants. Algae will bloom, filtering the light and depleting the amount of oxygen in the water column, resulting in further ecological damage. Whereas phosphorus is mainly responsible for eutrophication in freshwater ecosystems, nitrogen is mainly responsible for eutrophication in marine and terrestrial ecosystems. Study the image on screen to help create a visual map in your mind of the interconnectedness of the environmental systems involved. Click the Why We Care button, then click Next to learn more about how scientists measure eutrophication potential. Before we begin exploring each impact category, let's start with some basic background modeling information. The natural environment is an extremely complex system. Substances that are released into the atmosphere, for example, might be blown by winds to different continents, broken down by sunlight, swept out of the air by rain, or react with other chemicals to form new substances. Almost always, multiple processes are at work before a steady-state concentration somewhere in the environment is formed. Modeling what happens to a substance as it moves around the environment is called fate and transport modeling. This modeling predicts the steady-state concentration form someplace in the environment and is the first step in what we call the cause-effect chain. For any substance to be toxic, it needs to come in contact with an organism. Humans, plants, animals. It might be inhaled, ingested, or absorbed through the skin. Exposure modeling is the second step in the cause-effect chain. The next step is to model effect, what actually happens to the organism, such as respiratory illness or cancer in humans, or the death of a tree, a plant, a fish. The effect will be dependent on the dose of the exposure, as well as how much the organism has already been exposed to in its lifetime. Effect modeling is based on dose-response studies. Finally, there is damage, the last step in the cause-effect chain. For human health, damage is expressed in a unit called DALYs, D-A-L-Y, Disability Adjusted Life Years. A daily is a factor of how many years a person lives disabled, YLD, years lived disabled, and how many years of life is actually lost, YLL, years life lost. Read about the terms midpoint, endpoint, and characterization factor in the definition boxes below. Then click Next and we'll look at each step in the cause-effect chain in more detail.